Davide Ballavio, sobre el cual puedo comentarles lo siguiente. Él es doctor en biotecnología de alimentos por la Universidad de Milán. En la actualidad realiza postdoctorado en el grupo de investigación de quimiometría de la Universidad de Milán, en desarrollo de una base de datos de estructuras moleculares. Cuenta con 17 publicaciones científicas internacionales. Ha sido colaborador de un libro de análisis y es conferencista y expositor reconocidamente a nivel internacional. Por lo tanto, como lo dije anteriormente, para la Universidad Técnica siempre va a ser un agrado contar con personalidades de este tipo para este tipo de congresos. Lo recibimos con sus fuertes aplausos.
Muchas gracias y buen días. La primera cosa es que me gustaría agradecer a los organizadores del Congreso por la oportunidad de estar aquí y en Ecuador, en Loja, y por la oportunidad de hacer esta presentación. El problema es que no hablo perfectamente español, entonces voy a hacer la presentación en inglés, pero vosotros tienen una traducción simultánea, entonces espero que no estén problemas. Okay, this presentation will deal with the multivariate analysis, and so with the multivariate statistics applied to food science. Sometimes when people think to statistics are scared, so I'm not going to show formulas. I'm not going to show theoretical aspects. I just want to do an introduction of what multivariate analysis is, and I want to show some application of multivariate statistics in food science. So we are going to see what is multivariate statistics. We are going to see two applications. The first one is the identification of the geographical origin of olive oils, and the second one is the shelf life monitoring of cheese. And of course, we are going to see some conclusions on this topic. Okay, what is multivariate statistics? Okay, look at this circle, this schematic circle. On the top, we have knowledge. So if we have some creativity in our brain, we can do some hypotheses, okay? And on the basis of the hypothesis, we can design some, we can design some experiments. The experiments give us the data describing the problem. And if we are able to understand the data, so if we are able to read the information encoded in the data, we can get some information. So if we have information, if we are able to understand the information, we can get new knowledge. And so we have this circle, okay? Knowledge, hypothesis, experiments. If we are able to read the experiments, we have information and new knowledge. Okay, this is the basic definition of what multivariate statistic is. It's an ensemble of statistical tools that are used to read, to extract information from complex systems. So it's a statistical approach for understanding a complex system. Now, what is a complex system? A complex system is a system where you have several variables, several parameters affecting this system. And an easy example is wine. I'm from Italy, and I like to drink good wine. But the quality of the wine is affected by several factors. So we have the grape, the soil, the weather that change every year, the technology of production, the area of production. All these factors, all these variables change the quality of the wine. So the wine is the complex system that is described by several variables. And we have to understand and monitor all these variables in order to understand the quality of the complex system, the quality of the wine. Okay, so we have this problem, this system, that is described by several factors. All these factors can have nonlinear effects, can have holistic effects, can have synergic or correlation effects. So maybe we have two variables describing our system, and these variables are correlated. And so there is a relationship between all these factors that describe. There is presence of noise, and there is presence of not important information, of information that is not useful for solving our problem. Okay, another example for food science is the production process. Okay, the production processes are complex systems because we have several variables, several parameters that affect our production process. And so we have huge data sets, so huge tables of numerical values that describe the process. These variables are often highly correlated, so there is a relationship between all these variables. There is noise in the data, there are missing values, and the processes usually require a fast interpretation. So we have a production process, and in this exact moment, we want to know if the process is good or not. Okay, so in each minute of the production, we want to know if the samples, the produced samples, are good or not. And so we need a tool, a fast tool, in order to interpret the process. Okay, multivariate statistics applied to this field that is called PAT, Process Analytical Technique, is a solution. Okay, so let's see an example. We have a production process with two steps, A and B. Okay, here we have the production, and process B is the distribution. And we have our samples that are produced and that must be distributed. But these samples must respect some quality issues. So this process is working now, okay? So the samples are produced, and for each samples, we can get a chemical fingerprint of the samples, for example, by means of this analytical technique that is near-infrared spectroscopy. This is a fast analytical technique, so in each moment, we have a chemical fingerprint of a sample produced in the process, okay? Then, we have a fast analytical technique, we have a fast mathematical model that is able to interpret this chemical fingerprint and is able to say us if the sample is acceptable, is good, or is not acceptable, is bad. Okay? So in each moment, I know if the process is working well or not. Another example in TAT for the process is this one. We can monitor not the samples, but we can monitor the parameters that affect the process. So in each process step, we can analyze physical and chemical parameters, for example, temperatures and pressures. So in each moment, we have a lot of data, we have a lot of numbers, and we must interpret this number in order to know if the process is good or the process is bad. And we can do that with multivariate statistics. We know if the process is working well or not. Okay? So, we have a problem with several variables affecting the problem. The first point of multivariate statistic is that all these factors, all these variables are monitored, are considered at the same time. So we don't analyze the first one, the second one, the third one at a time. We consider all these variables in one moment. First. The second is that these statistical tools are able to extract useful information from the data. So we have huge data sets, huge tables of numerical values, and we can see what's going on. And this is really important. The third point, the last point, the approach is we have data in, and the output are graphics. So the approach is data in, graphics out. So we have these huge data sets of numbers. We put these tables of numbers in a mathematical model, in our laptop, in our computer, and we are able, the mathematical model gives us a graphic where we can read at least all the information that is contained in the data. Okay, so it's easy to see what's going on because we have graphics that are easily interpretable. Okay, these are some fields basically where you have a numerical tables with values, you can apply these methods. Okay, so for example, analytical chemistry, spectroscopy, environmental chemistry, pharmaceutical science, of course, food science. I did my PhD thesis in food science. So multivariate statistics applied in food science. Then we have toxicology, medical diagnostic. We have seen yesterday a presentation where statistics were used to understand if food samples was good or bad. The quality control and the process control, the environmental control, agronomy, geology, social science, and so psychology, for example, image analysis. All these fields require multivariate statistics. What about food science? For example, if you have an analytical technique that you use for analyzing your food samples, then you get data. And you can use these methods in order to understand the property of the food samples. Or another application is the sensory analysis. So where you have a panel of assessors, of human assessors, that taste a food product, give a quality response, and in order to understand what's going on, we can apply these methods. Okay, this is a search I made on internet. There is a database of scientific papers that is called Scopus, and I did this search by searching in the title, in the keywords, and in the abstract of the papers, the words food multivariate analysis and chemometrics in the last 20 years. Okay? And you can see that the production, this scientific production is increasing. Okay? Why? Maybe because now it's more easy to publish a paper, because there are more journals, because there is internet, but probably because now we have more computational capabilities. So 20 years ago, it was difficult to develop a mathematical model. Now it's more easy. We just need a laptop. Like now there are more data available by internet, for example, or because we have analytical techniques that are more fast, and so we have more data. And the third point is that now we have more complexity. So we are solving problems, but usually when you solve a problem, you find a new problem, a deeper problem that is more complex. Okay? And so we need these tools in order to understand what's going on in a complex system. Okay, this is part of the circle of the knowledge. We have hypotheses, we build some experiments, and we get data. Okay, these are all the multivariate methods that we can apply. The first one is the experimental design, that are statistical tools that are used to optimize the number of experiments we are going to build. Okay? So before going to the lab, before doing the experiments, we can design an optimal number of experiments by means of these methods. Then we can do experiments and we get data, numerical values. And we can analyze these values on the basis of the goal we have in our problem. The first methods are methods for exploring the data, okay? And the most famous is this one, PCA, Principal Component Analysis. And we are going to see an example later. So imagine these huge tables of numbers where each row is a sample and each column is a variable describing the sample. These methods consider all these huge tables of numbers at the same time and can give us information about the relationship between the samples, the relationship between the variables, and also we can know how the variables affect the samples. Okay? And this is really popular, let's say. Then, okay, optimization, but the most important are regression and classification. So, we have our data, and we can build a mathematical relationship between the data describing the complex system and a quantitative response. In this case, we use regression. So we are going to build a relationship, and so we are going to study the relationship between the data and a quantitative response. If the response is qualitative, we can use classification. So for example, in the process example before, we saw that the final response was acceptable, not acceptable. The process is good or the process is not good. This is classification because we have a qualitative response. Okay, good, not good. Okay, by means of these methods, we interpret the data and we get information. Okay, let's see some application in food science. Okay, the first one, this was part of my PhD. The first one is the geographical classification of olive oils. Now, olive oils is an important production in Italy. We have a lot of olive oils. Another important thing is that now in the European community there is a regulation that permits to label all the samples with this label, denomination of protected origin. So if we have a production of olive oils that has quality and that is located in a precise place, we can use this label, denomination of protected origin, for our sample. And this label gives us, give the samples of olive oils more value, economical value. Okay? So, in Italy, there is a lake in the north-east part of Italy that is called Garda, and there is a small production of olive oils. And these olive oils has this denomination of protected origin. So basically are oils of certified quality. Okay? And the producers of these oils wanted an automatic tool that was able to distinguish, to characterize these oils that are quality oils from oils produced in other regions of Italy and of Europe, on the basis of a chemical fingerprint. So we have oils from Garda, we have oils from other areas. We can describe these samples of oils with a chemical fingerprint, with the chemical parameters, and we are going to see if the oils are different. Here the analytical method was the electronic nose, And the statistical method was principal component analysis, ranking methods, and classification methods. Now, what is the electronic nose? It's an analytical method that simulates the human nose. Okay? So, an electronic nose gives us a chemical fingerprint, a chemical profile that describes the samples. Okay? And an electronic nose is usually made of different sensors. And each sensor is linked to a specific class of compounds. So, what we can do is to select the sensors of the nose that are more able to distinguish our olive oils. Okay? Okay, the data set has included 53 samples of olive oils. 56 samples were oils from the lake of Garda, and 17 samples were oils from other regions. For each sample, we collected the signals with an electronic nose, the signals of 15 sensors. Okay, so for each sample, we have 15 chemical profiles. The goal was, first, see if the olive oils from Garda and the other oils have a different chemical fingerprint, and second, to choose the sensors with more discrimination capability between the oils of Garda and between the other olive oils. Okay, this is an example of the chemical profiles. So each line here is a sample of olive oils, and these are all the profiles detected by the first sensor. Okay? All these ones. And we can collect this data in a data matrix, so in a table of numerical values. Then we can do the same for the second sensor. Okay? And we can collect another numerical table. And we can do all this for all the sensors, and we get this cube of values, of numerical values. Okay? Now, this cube is the description of our complex system. It's not possible to understand what's going on here by looking these values, because we have a lot of values. Okay? So we need a statistical tool that is able to interpret the information encoded in the data. So here we applied multivariate analysis, and in particular PCA and this method that is a ranking method. It's not important now which is the theoric approach. Okay, there is this multivariate model. There is this mathematical model that is able to describe the information of this data. With this model, we can get information, and we can answer to our questions. Okay, this is the first result. We have 15 sensors, and here you have the 15 sensors. For each sensor, we get a numerical value, is a discrimination index. So the first sensor gets a discrimination index of 4. The second one, a discrimination index of 4. And the third one was significantly higher. Okay? So here, we have encoded the information. It's not important how, now the calculation, but just look here. It's easy to see that these two sensors are different from the others. And these two sensors are with a statistical approach. These two sensors are the sensors that are that have more discrimination power. So we can look the first sensor MOS 111 and the second one MOS 112. Okay. If we look the raw profiles, the original data, this is the first one and this is the second one. Each line is a sample. The blue lines are the samples from Garda, the good olive oils. The red lines are the samples from all the regions. Here, for example, on the left, you can see that the shape of these tubes are different, okay? So, here there is a chemical difference between the samples, okay? So, there is a chemical difference between the oils belonging to the Garda Lake and the other oils. Okay, this is not enough, so we can apply PCA, principal component analysis, to the data. Principal component analysis is a method to reduce the data dimensions. And so we have these huge tables of numbers, but we can look at the information in just one graph, okay? So here on the left, there is a plot, a three-dimensional plot, that describes all the information we have in the data, okay? And each point here is a sample of olive oil. Each white point is a sample that is not Garda, not quality. Each black point is a sample from Garda. So here is possible to see all the information, and it's possible to see that by using all the available information, all the sensors of the electronic nose, there is a trend of discrimination, okay, here, but it's not good. Here, if we repeat the analysis, the PCA, by using the two selected sensors, there is a much better discrimination, okay? So first, we were able to discriminate the samples on a chemical, with their chemical fingerprints. And second, we were able to choose the sensors with more discrimination capability, okay, with a statistical approach. Okay, second application is the shelf life monitoring of cheese creams. These cheese creams were mascarpone creams. I think you have mascarpone in Ecuador. We use it usually to do tiramisu. Okay. So the goal was monitor the quality of these samples during the time. Okay. So how the properties of these samples change during the time. The analytical method here was a rheological method. So we used the mechanical profiles of these samples, and we used principal component analysis. Okay. Now, so we have these mascarpone samples. For each samples, we get a mechanical profile that describes the mechanical properties of the samples. These profiles are usually parameterized, but we can analyze all the profile by means of multivariate statistics, by means of PCA. Okay, so our complex system here are these mascarpone samples described by these mechanical profiles. Okay, this is an example of the profile. These analyses were made by some guys in the University of Milan, and they gave me the data, and so I don't know exactly this rheological method. But basically you have your sample, okay, and you make a pressure on the samples during the time, and you register the applied force on the sample, okay? And what we did is to repeat this analysis, okay? So we get the mechanical profiles for fresh samples, and then after 1 week, after 2 weeks, 3, 4, 5, 6, 7 weeks, okay? So we can see during the time which are the changes of the mechanical properties of these samples. So we have collected all these mechanical profiles in a numerical table, okay? That is the starting point for multivariate statistics. We have this huge table of numbers describing the mechanical properties of the samples during time. And we have to analyze, we have to understand what's going on, okay? Now, it's not possible to do it visually, so we can apply PCA, and we can see all the information encoded in this matrix. We can see all the information we have here in our data in one plot. Okay, that is this one. So, this is the result of the principal component analysis. Here, each number represents a sample of mascarpone. So here we have all the fresh samples. Okay? Here we have all the samples after 1 week, after 2 weeks, after 3 weeks, and so on. Now it's easy to see here that there is a trend on the first axis. So we have fresh samples here, and we have old samples here. Okay? So we can monitor the changes of the mechanical profiles here in one graph. Second, we can see that the fresh samples are more clustered. Okay? The old samples are more far. This means that these samples have the same mechanical properties, and here the mechanical properties are changing. Third point, we can see that there is a strange thing here, because we have fresh samples, we have this trend of increasing time, but here we have something strange because this group should be here. Okay? So why? Okay, here we can see all the relationship between the samples, but now we want to know why there is this exception. So we can analyze the mechanical profiles. Okay? Okay, this is a result of the PCA, is the meaning of the mechanical profile on the data set. Okay? And if we compare this result of the PCA with the raw data here, it's easy to understand that the meaning here is fresh samples have low mechanical profiles. Old samples have higher mechanical profiles. Okay? This is the meaning of this graph. And so, with one graph, we can understand the meaning, the behavior of the mechanical profile during the time. The second result. Here we have this plot, that is the plot related to the second axis on the first plot we see. And we see that there is something strange in this area. Okay? So after 20 seconds of the mechanical profile, we have something strange. Okay? But this area is related to this area in the raw mechanical profiles. And so there is something strange here when you have the decreasing part of the mechanical profile. Okay? There is something strange. We can understand why. Okay, this group here is different. Okay? This is the strange group. This is the same plot of before. This group is strange, and this group is different on the second axis. Okay? So this group is different from the others in this part of the mechanical profiles. Okay? And it's clear why, because there is a shift, okay, of the mechanical profiles of this group with respect to the others' mechanical profiles. So, with 3 graphs, we can see the relationship between the samples. Okay, so we can see the trend here, and we can understand why there is this behavior and there is this strange group. Okay, so we have our complex system, but we are able to encode all the information in 3 graphs, and understand what's going on. So basically, data are the core of multivariate analysis. Okay? This is a data set. Okay? Numbers. This is a data set describing a problem, describing a complex system. And we have to understand what's going on. We have to extract information here. Now, first, it's not possible to read the information here by looking at this table. Okay? This is clear. Second, if we analyze, okay, now imagine that here each row is a sample and each column is a variable describing the system, describing the samples. It's not possible, if we analyze the first variable, we can make a plot. Then we can analyze the second variable and we can make another plot. But if we have, let's say, 100 variables, we'll get 100 plots. And it's not possible to see what's going on first. Second, if we analyze a variable at a time, we don't see the relationship between the variables, and we lose information. It's more easy, it's more fast, it's more economic to read all this information together. Okay? So, we have data, in the data we have information, and usually information is made of noise, and we don't care about noise. It's made of redundant information, it's made of useful information, but here is made of specific useful information. And so information that we need to solve our problem. So, for example, in the previous example of the electronic nose, we had 15 sensors, but we were able to select the specific useful sensors for discriminating the olive oil sensors. And so, here, our goal is we have a lot of data, a lot of information, but our goal is to use a statistical approach to select this part of the information. Okay? Now, how to do that? Until, 20 years ago, but often still now, there is a sentimental selection. So we select the information with our heart. And so, for example, we have a lot of variables, but on the basis of our experience, on the basis of the tradition, of the opportunity, of our personal knowledge, we select 2 or 3 variables that we love, that we like. Okay? Okay, this is, first of all, it's dangerous, and second, it's not useful to read the information. Okay? So the basis is we have to use a statistical, mathematical approach, okay, in order to understand what's going on. So, again, information, we can select the relevant information. But if we have, we can collect our data. And, but if we collect the data in a wrong way, we get bad data. Then we can apply the coolest, the new statistical approach. But if we have bad data and a good statistical approach, the results are bad because we don't have good information. And the opposite is the same. If we have good data, so we have collected the data with a lot of work, but then we don't have a good statistical approach, it's not possible to understand what's going on. Okay? So we must have good data collected in a good way. We must apply a good statistical method, and in this way, I can assure you that we can get good information. Okay, this sentence is a resume, and it's really important. It says, what I've encountered is that a lot of highly skilled people refrain from using all their available data. Data which have been collected with substantial effort. So, sometimes we go to the lab, we do a lot of experiments, we spend a lot of time, we waste a lot of money, and we get a lot of data. But then we don't know what to do, okay? So we have spent a lot of time and money. We know we have this data. We know that there is information in this data, but we don't know what to do with this data, okay? So, last slide. What is multivariate analysis? They are statistical tools able to resolve problems connected to complex system. So, system where you have several variables affecting, describing the system. The first point is that in these tools we have data in and graphics out. So, we have a lot of numbers, we put the number in our mathematical model, and we get graphics that we can use to interpret the data in an easy way. Second, multivariate statistics is cheap because we need just a laptop now, and it's fast because if you want to, I don't know, to calculate PCA, principal component analysis, the algorithm requires less than 1 second, okay? So cheap and fast. This is important. Multivariate statistics requires know-how, and so requires how to work. But, for example, I'm not a mathematician, and I'm not a statistician, but I can work with these tools. Because the important thing is not to know the theoretical approach. Okay, so it's not important to know what's going on in the algorithm exactly. What is important is to know basically what the method does. It's important to prepare the data for the calculation, and it's important to know how to interpret the graphics, so how to interpret the results. Okay, so if you are not a statistician, it's not important. There is nothing impossible and there is nothing difficult, okay? So, needs know-how, but is needed when we deal with the complex system, okay? Because if we don't use this method, we cannot resolve the information encoded in the data. Okay. Okay, this is it's the work group where it's the research group where I work. This is my boss, Professor Roberto Todeschini. As you can see in Italy, I'm the tallest one too, okay, here. Okay, this is my email. So if someone of you is going to work or wants to know something more, you can feel free to write an email. And this is the website of the research group, where you can find all the stuff related to chemometrics and multivariate analysis. Basically what we do is chemometrics, multivariate analysis, and molecular descriptors that are methods used to encode the chemical information of chemicals, okay, of drugs. Y en español, gracias por vuestra atención. ¿Puedo responder a la pregunta en español? Vamos a probar. credo utile. No, io tengo... Bueno, claro.
Por favor, las señoritas de protocolo están haciendo llegar papeles donde pueden recetar, enviarnos sus preguntas. Tenemos 20 minutos para esto, por favor.
Quiero...
Nos están preguntando cuál es un límite aceptable para ruido en los datos.
Dipende dall'applicazione, ruido is noise, okay. Dipende dall'applicazione, perché, por ejemplo, una aplicación en la ciencia de los alimentos es el sensory analysis. Entonces, por evaluar la calidad de un producto alimentar, es posible utilizar un panel test de hombres. Y en este caso, el noise, el rumor, el ruido es muy alto, porque tú debes modelar alguna cosa que es humana. Entonces tú tienes mucho noise, porque el comportamiento humano no es fácil de modelar. Si tú trabajas con datos analíticos, entonces con una técnica analítica, tú tienes un rumor menor, más pequeño. Entonces depende de la aplicación. Por ejemplo, cuando tú haces un modelo para la evaluación de la sensory analysis, usualmente el 40% de información explicada es mucha. Cuando tú haces un modelo por la calibración de un instrumento analítico, tú quieres mucho más.
Nos preguntan qué otras aplicaciones tiene el análisis multivariado, digamos, para trabajos en empresas pequeñas. ¿O solo sirve para investigaciones? ¿En procesos se puede usar o solo investigación?
Es utilizada para investigación, claro, para todo. Entonces, están aplicaciones en la empresa. Porque también nosotros en la investigación tenemos problemas, pero también las empresas tienen problemas. Y entonces, una empresa que... por ejemplo, por el proceso de producción, esto es un claro ejemplo de aplicación en la empresa. Por ejemplo, están muchas aplicaciones en la empresa farmacéutica, pero también en la empresa alimentar, por ejemplo, por los estudios de nuevos productos alimentarios. Entonces, por el desarrollo de nuevos productos alimentarios.
¿Cuáles son los softwares o herramientas computacionales que se usan para trabajar en quimiometría, análisis?
La primera parte de la pregunta.
¿Qué software se usa? ¿Qué software es el más usado?
Existen muchos softwares. Bueno, malo, complicado y fácil. dipende dal livello di applicazione. Entonces, el más famoso es MATLAB, donde tú puedes modificar los algoritmos, pero no es fácil por la utilización. Pero en Internet ahora está toda una comunidad de open source, entonces tú puedes buscar software para hacer multivariate análisis gratis. Credo que el más desarrollado es un software llamado R, okay. Pero que es similar a MATLAB, entonces no es más fácil de utilizar, pero están otros software y tú puedes buscarlos en internet gratis.
¿El análisis multivariante sirve como herramientas para hacer de control de calidad, digamos, en alimentos? ¿Sirve para buscar cuál es el control de calidad, digamos, en vitaminas?
En vitaminas.
Vitaminas.
Si tú puedes, sí, creo que sí, porque si tú tienes, creo que sí es un ejemplo de regresión. Entonces tú tienes las muestras son descritas da un parámetro químico, da una chemical fingerprint, y tú tienes el contenuto de vitamina. Es posible relacionar con un modelo matemático la descripción química de las muestras y el contenuto de vitamina. Y entonces es posible en el futuro utilizar este modelo matemático para predecir la respuesta, entonces el contenuto de vitamina o la calidad vitamínica.
Nos preguntan si se puede utilizar este tipo de herramientas estadísticas para el diseño y desarrollo de un producto que tenga una condición o una formulación dada.
Sí, es por ejemplo, esta es una aplicación típica del diseño experimental, donde tú puedes monitorar el efecto de todas las variables sobre la calidad final del producto, ¿ok? Entonces tú puedes evaluar cómo el efecto de todas las variables sobre el producto final y con un diseño optimizado. Entonces, no casualmente, algunas veces, la tendencia es de probar, ¿ok? Entonces probamos a modificar esto, probamos a modificar esto. Si tú tienes un approach más objetivo, tú puedes optimizar el producto, en este caso la calidad de un producto, evaluando todas las variables, todos los parámetros, con un approach, una vía más segura.
Bueno, como no tenemos más preguntas, le agradecemos a David por su explicación.